Okay, so far in our study of acids and bases, we've looked simply at what happens when I put an acid or a base in water and how it interacts. For example, when I put acetic acid in water, I get hydronium ions and acetate ion. We've also learned about how salt solutions can be acidic, basic, or neutral. So if I just put acetate in water, that becomes a base. So now we're going to look at what happens when acids and bases interact with each other and not just what happens when an acid or a base reacts with water. So we're going to start off with this question. What happens to the pH if a hydronium ion is added? Well, according to Le Chatelier's principle, if I add some hydronium, then this reaction should shift left to consume the hydronium and produce more acetic acid. So remember, hydronium is a strong base, a strong acid, Acetic acid is a weaker acid, so its pH isn't as low as that of hydronium. And we're going to use this idea of Le Chatelier and turning a stronger acid into a weaker acid when we explore buffer solutions. So, what is a buffer solution? A buffer solution changes pH only slightly when small amounts of strong acid or strong base are added. And that's the key. Strong acid, strong base are added to a buffer solution. The pH is fairly stable. This has a lot of applications in biology and elsewhere. So, to make a buffer, you have to have significant concentrations of the acid and its conjugate base, or you could phrase it as the base and its conjugate acid. Either way, you need a significant concentration of both species in the conjugate pair. So when we look at this equation, if we just put acetic acid in water, remember the amount of acetate produced and hydronium produced is very small in relation to the amount of acetic acid I started with. But if I make a solution where I have both acetic acid and acetate in significant amounts, which means I put them both in one container at the same time, then I form a buffer solution. Okay. And what happens with the buffer is the weak acid will react with small amounts of hydroxide to form the conjugate base of the weak acid, which itself is weak. So it lessens the impact on the pH of the hydroxide by changing it into something that is weak instead of strong. And the same thing happens with the weak base part. The weak base interacts with hydronium to form the conjugate acid, but again the conjugate acid isn't as strong as a strong acid, so I don't get nearly as much H3O plus in solution. So that's how a buffer works. Graphically we can illustrate this by looking at two different containers. A container that has 1 liter of pure water. The pH of pure water is 7. You can see that right here. If I add a small amount of hydroxide, so the concentration of this, if I have 1 liter, this would be 1.0 times 10 to the negative second molar hydroxide. You can see the pH jumps all the way up to 12. Likewise, if I have a solution that is 1.0 times 10 to the negative second molar in hydronium, the pH is 2. So very acidic. But if I start off with a buffer solution that has a pH of somewhere, this is probably about 4.7. Oh, excuse me, I was looking at the wrong one. Here's my buffer. My buffer solution right here, that's probably about 4.5. So here's just my buffer. If I add hydroxide to it, you notice the pH goes up a little bit to about 4.7, but not nearly as much as it does in pure water. And that's because I have a conjugate acid that is a weak acid that's reacting with the hydroxide and changing it into the weak conjugate base. And the same thing happens if I add the same amount of hydronium. it goes down a little bit, so we could say this is like 4.3. But again, the pH remains fairly stable when compared to what happens to the pH of water. So if we want to make a buffer solution, we follow these points here. So a good buffer, we want a relatively high concentration of both the acid and conjugate base. That way there, it will be pretty robust and not break down just as soon as a small amount is added. Okay. And it's most effective if the concentrations of the acid and base are about equal. And to determine what acid-base pair I should use, I should look at the pKa of the conjugate acid I want to use. So if I want a pH of 5.0, let's say, I would want to find an acid whose pKa, negative log of Ka, is close to, is about equal to 5. That would give me the best buffer. And then I would use that acid and its conjugate base. So even though buffer solutions resist changes in pH, they're not totally resistant across a wide range. So there's only so much strong acid or strong base that a buffer can actually neutralize, and the amount it can neutralize without really changing pH is referred to as the buffer capacity. Okay, so if you have relatively high concentrations of the acid and the conjugate base, you are increasing the buffer capacity. If the conjugate acid and base is nearly equal in concentration, you are increasing the buffer capacity. So let's take a look at some math behind a buffer, because that's really what we're interested in. If we want a pH in a certain range, we're going to have to do math to get that.